Welcome back, everyone, and this is going to be probably the final IK solver video I'm going to be creating, because this pretty much rounds out a lot of the functionality I kind of wanted to build, so I can start moving forward and start doing other things with our IK chains and stuff. So as of right now, you can see here's my demo file, and we're on our fourth IK solver, which I really don't know what to call it. I'm just calling it the 3-bone solver. I also thought calling it the hind leg solver, because it's kind of modeled after the idea of having like an animal leg, like you know, like a cat or a dog, and so they have like 3 bones in how they animate. So as you can see here in the demo file, you know how it kind of just folds in on itself, and then when it needs to, it just reaches out and then kind of folds right back in. So. So yeah, that's the next and final one. I was thinking about maybe doing a different one in case there's ever a virus problem. But yeah, so let's work on this one. This is kind of I thought this was going to be the hardest one to do, to be honest, because again, let me get rid of that. I thought this was going to be the hardest one to do, simply because of Google Online. Like, first, I can't even find a good name for it, and number 2, no one ever does anything. Like I see like Maya, they have these solvers, but no one has it in code-wise. So, and of course, you know, no one has an answer for this. So it's always one of those things where you kind of have to figure it out on your own, for the most part. So I came up with a really cool idea about this. Let me see, how do I draw this? So let's draw this. So this is our leg. This is our animal leg. So we have 3 bones. So like, you know, in the last video, I think I did something that I didn't like. Made it hard for you guys to understand. So I'll try to label things. That's bone 1. Sorry, that's bone 0. This is bone 1, and this is bone 2. Okay, so there's our 3 bones, right? And again, this is an IK solver, so we have an end target. So this point right here is our end target. So that's where we want to end, and this is where our hip is, where our leg is essentially attached to. So it was kind of tricky to figure out how to do this, but then what I was doing one day was I was just drawing. So I know that my end target, my target length has to be this way, right? So I need the start of my point. That's the start of my chain, and this is my end effector. That's where I want the chain to finally reach its end. And it took me a while to realize that this is actually a specific shape. If I were to, like I did on a piece of paper, I did this. I started like putting dots instead of dashes. You know, you might like, oh, it's a diamond. Well, it's not necessarily a diamond. It's a parallelogram, or some type of trapezoid. Like sometimes it ends up being like this as well, depending on the bones. Like right now, all the bones are even, so they make like a parallelogram. But if the bones are uneven, they kind of create some kind of trapezoid. You know, it could be like a little, you know, it could be like any weird trapezoid type of size. So I was like, oh, okay, well, that's kind of interesting. And the one interesting thing about when you like look at this in the dots and you start paying attention, there are, you know, when you start paying attention to how these shapes are, there's one thing they have in common, because they're all kind of like these square shapes, and square shapes and rectangle shapes have a cross section, right? They all have cross section, even though the sizes are different. They all have cross sections. So, okay. So there's a cross section. Now, in the code I did, I think it's probably slightly incomplete-ish. because sometimes the cross section, like the idea is, we know, like when it comes to these shapes, like if we compare the two, we know that's one bone, that's another bone, that's another bone. So let me just highlight it a little bit. That's 1, that's 2, and that's 3. Same thing with this one. Even though the shapes, the lengths of the bones are different, it's all there. It all kind of connects. It always makes this one shape when you're kind of dealing with an animal leg. Now, not all animal legs are the same, but a lot of them have this general idea. Like I was trying to look at them, and some of them have that general idea. Now, what I say why mine's incomplete is because the way I do it is that, you know how some of these, like if it's a parallelogram, the cross section always meets at the center of each cross section. If everything's kind of even, even though this does work for uneven bones, I still use the middle point kind of as a hinge, like as a hinge to actually solve for things. So in the previous video when we were doing like the piston, I probably should do like a ratio. You know, like because like we need like the idea is that we know it's a parallelogram, it's a trapezoid. What we need now that we know it's basically a square or rectangle, it has multiple triangles, so we can define everything as a triangle. So that's, you know, here's the midpoint. So what we need to do is figure out this angle, and we need to figure out this angle, right? So I already do a kind of a ratio already, but but like I said, for the center part, like the center bone, I kind of split it in half. I probably should use a ratio of how much of the bone I should be using to make it a little bit more accurate. But, you know, that's something I can do further on for more optimization if I start dealing with bones that are having very much more specific and I want to optimize their movements more. But for this video, and really just to show you the general idea of how to do this, I'm just going to divide the middle bone in half and treat that as a half. So this way I actually have, like I said, 2 separate triangles. So yeah, and I forget what the equation. I have to look at the code, but we know, like I said, we know the length of bone 0, right? We know the length of bone 0. We know the length of bone 2. We know the lengths, and we actually know the length of bone 1, the centerpiece. Like I said, we're going to cut that in half. So we're going to create that triangle at that center point. So this way we can say, well, one side of the triangle equals to 1, the other triangle equals 1 and the half of 1, and then some ratio of our target length. And the same thing for our second angle. We have half bone 1, the whole length of bone 2, and then some ratio of the length, the target length. So this target length has to be divided because it can be different depending on the size of the bone. So like I said, I did test it for multiple bone lengths and it does work fine, but I guess I could improve it. So like I said, I can have like a really small, oh, this is the eraser end. So I can have like a small bone, another small bone, and then a really long bone. And then, but I could kind of end up making it somehow go to the center and then curve. So it's not like a perfect straight line the way I'm doing it. But like I said, if I were to do this correctly, I would do it. But in all honesty, it doesn't. I don't think it really matters, to be honest, if I choose the middle or not, because let me see if I can draw a better version. Because I actually don't think it matters. Like I don't think it really does matter. Because it's the angles I'm looking for. So So this, this, this. They're curved. But like I said, it's really just this angle I'm worried about. So it doesn't really matter if I have a triangle here, because that angle doesn't change. So it doesn't really change. Like, and same thing, it's this angle. As long as I get whatever value here and whatever if I get whatever value for this side of the triangle, for whatever this, as long as it's kind of evenish, I'm gonna get the exact same angle regardless by using the law of cosines, and the equation is the SSS one. So this way we can get the any angle of a triangle as long as we know the lengths of all three sides. So that's what I said. So once we know all three sides, we can then solve for whatever angle. And like I said, the specific angle it is, I guess it doesn't really matter if I actually do the center, or be more correct by using a ratio of like some kind of scalar of that bone to make it a little bit more even. So when I do that line from start to finish, it's like more complete. It's more accurate. But we don't, like I said, we don't need to be accurate. We have to be. We can be as close as possible. Whatever makes it easier, right? You know. So like I said, the center worked out really well for me. I don't need to go any further than that. But keep in mind, if you're trying to get something to be more accurate, maybe you want to take that extra step and the extra math and make the center bone, the length of it, more dynamic in relationship to the triangle you're trying to solve. Yeah, see? So that's essentially it. That's really the magic trick into solving the three bones. Is like you just treat it as a trapezoid or a parallelogram, one of those shapes, and then just kind of try to figure out a way to divide them into two different triangles and solve for two different angles. And it works out. So if I go three bone solver. So right here I have here's the three bone solver already working, and you notice each bone is slightly longer than the next. So like I said, even though I'm using the center bone, this probably can fold a slightly bit better if I did a variable. But if you have a character that's animating this movie kind of fast, you probably wouldn't notice, because everything tries to fold more evenly, but it's because of the center point of the middle bone. So if I were to, like I said, make it more variable, it probably would fold in a lot neater. It should fold in more evenly, but it's not, because it's the lengths are wrong. But like I said, I'm not sure if it really matters or not, but there's a slight improvement that could be done to this. But like I said, this is good enough. Like I said, you won't notice it. Like if an animal is running, you won't really notice that the bones aren't folding in absolutely perfect as much as you want. Like I said, there's always room for to make it a little bit better, more optimized. Let's see, we got 13 minutes already, so let's look at the code. So a lot of the code is the same. I don't have to describe it. Everything's animating, so I can probably just unanimate everything for now. And let's see. So we have the three bone solver. We do the exact same scale thing we did before. I have a to-do here. Like I said, this kind of is partly incomplete, but I don't want to go too far with this, because I'm not going to do anything with animal legs. And what I have so far, I think, to me, is good enough for what I'm planning to use it for the most part. Once I start doing a lot more quadruped, like wolves and dogs, and when I start doing, once I start trying to animate more animals, I'll probably come back and try to revisit this solver and improve upon it and make it a little bit more accurate. But until now, like I said, it's good enough. Gets the idea out. Like I said, like in one video for the circle arc, I said, yeah, as long as the information is out there, the collective can always come and improve upon it and make it better. So, like I said, I want this information out, and then you guys can improve upon it before I get a chance to, as long as you understand the information. So, like I said, the first step, once we have all that scale and whatnot, the usual crap I haven't written every single solver I have, just to check the scale and position to see if I need to fully extend it or not. This is kind of boilerplate, really. I should probably make this into a function, because it's pretty boilerplate. functionality. But again, that's another step of optimization. All right, so the first thing we need to do, like I said, is figure out first get all our lengths in place. So we have all our bone lengths. That's fine. And then create a little equation on how to get that ratio between for that target length. Like how much of that target length is the bottom triangle going to use, and how much is the top triangle going to use. So so I create the ratio for the top. So like I said, bone 1, I want half of it. So I got bone 1 of half plus bone 0. Divide that by the total bones. And you might be like, why am I not just using chain.length? Just in case down the line I want to apply this to a specific part of a chain. Let's say let's say for an animal leg, there's 4 points in the chain. Like the bottom point is like the toes. For like a cat, you have the little toe bone. But I just want to apply this to the 3 bones, so that's why I'm doing this. Instead of using chain.length like where I do for other solvers, I'm purposely creating the length of just the 3 bones I'm working with. That's probably why I end up calling this the 3-bone solver, because I'm going to specifically only target the first 3 bones of any chain. So it doesn't matter how much chain it is, which I did it anyway. Yeah, I did it anyway, but like I said, there's slight improvements. I can probably do this, make that equal chain length, whatever. But whatever. I mean, if my chain has 3 bones, this is not a big issue. So it really could be this here as well. But these have to be in parentheses, because else it'll multiply these 2 and then add these together. But for now, since I have a chain of 3, I'll just leave this in here as a bug for future when I try, because right now I'm not really have a chain of 4 or 5. That's something I want to do in the future. So like I said, this code is kind of partly being written for that future possibility. Sometimes when you program, you kind of have some idea of the future, and maybe just kind of prepare for it a little bit, just in case. Sometimes I don't want to do that and just write the code and then deal with it later, but sometimes I kind of half-ass it. I prepare for the future just a little bit. I don't want to go too crazy with it. So, all right. So, like I said, it's the total length, which is just chain length divided by this, gives me the ratio that I need. So this way I know how much of that length of the target length I can use. So I get the target length by using the scale value, so I know how long it is. And for the law of cosines, the SSS version, that is the equation. So it's a squared plus b squared minus c squared divided by 2 times a times b. So I kind of just plot the bones where I think they make the most sense, because I want to solve for c. I usually try to make the variable length over here the c value, so when I want to solve for, like if I call like this side c, like the side that's variable, that's scaled, if I say c, then this equation works for the opposite angle of it. So that's why I kind of make sure that ratio 1 is c and everything else is a and b. And then I do the equation, but then I clamp it. Now it's important for clamping because this value can accidentally go outside the range of -1 and 1, because cosine of c. So cosine of c equals this. But if I want to get c, which is the actual angle, I need to use arc cosine. So the final value, I guess I just dump it into a variable called n, like just for a number. I have to clamp it, because if you put in a number into arc cosine that's outside the range, you get back an NaN error, and you don't actually get an error. Like the JavaScript doesn't crash; it just treats NaN as a number value, and then everything kind of just gets screwy, and it's hard to debug. So just keep that in mind when you're using arc cosine, or don't put a value that's beyond that range. You always have to clamp it between -1 and 1. So just keep that in mind. So once I have the end result of an angle, I pop it into arc cosine. So this way now I actually have the actual angle that for that triangle. Then I subtract that angle from math.pi, and I have the perfect angle. And I repeat the process for the bottom triangle. It's the exact same code. Some people might say, why don't I just create a function that does this? Because I don't want to call a function twice. I'm not going to do this that often, and it's such a little bit of code. There's no reason for me, like if I'm doing like a bunch of solving, like if I have a bunch of animals on the screen, I'm animating them, and it's just one less. It's two less function calls. So that's why. So in case you have that notion, like, why am I not making this a function? Why am I repeating code? Because sometimes repeating code is more efficient than having functions. Efficiency and ease of reading aren't always connected. Sometimes optimized code looks like shit. It does. It looks like crap. It's hard to understand. Sometimes hard to read. Sometimes even hard to maintain. But if you really care about efficiency, sometimes you have to get really ugly. So this was kind of ugly, but like I said, I don't need another function. I don't need to call another function. It's not too hard to maintain. It's just a little ugly. It's a little repetitive, but it's only for 2 bones. It's not like it's variable where I'm doing like 20 bones or whatever. So just so in case you look at this, why am I making these weird coding decisions? So you guys understand. So now that I have the 2 angles, by using the law of cosines, I aim the first bone. There's the angle of the first for the top bone, or for like bone 1 will be at angle that, and bone 2 will have that angle but in a negative. We just go the opposite. Works out. Like over here, you see I had code commented out because originally I was creating a quaternion and then setting it. But the first bone is being rotated, so I don't need to create a quaternion at all. Well, I don't need to create a quaternion and then multiply. I can automatically just set the x-axis and then the angle that I want to go to on the rotation itself. So I was able to optimize it a little bit further just by using my aim direction, and I cover this in the circle arc video, so I'm not going to go back into that. But just so in case you see the comments, I like to leave things like that just to remind me why certain things are the way they are. And then at the end, we kind of just realign everything. Like I said, in the 2 videos ago, I went forward and showed you the code and explained a line forward. But a lot of the times when I create these IK solvers, everything's at the right place, but the first bone is not aligned correctly. So where the end of the chain is not touching the target. So this just realigns everything. So again, and that's it. And there you go. And that's all the code to it. Let me go back. And I can animate this again. So you can see it animate. Like I said, this example uses uneven bones. And folds, like I said, folds pretty well. Most often you're going to be folded all the way anyway when you're running, so you won't notice it. But if the bones are more even, they will then function just well. Like I said, it's just that little ratio that you can probably change to make things work better. So let's say if I take out this addition and make the bones all even, and make the target animate a little further, because now the bones are smaller. I can use a 35, which does a good job. Refresh. You see, now you notice that everything now kind of folds in much more evenly. So this is perfect, like I said, because everything is even. So I'm using the center of the middle point as the pivot point, but based on the ratio I should change. Also, probably apply the ratio of how much of the length of the center point I should use for my triangle lengths. So this way, I probably get a much better rotation when dealing with more variable length. So I know how to fix it. I just didn't want to bother to add the complexity to it. Like I said, you can always make things, improve things, but is it worth it? And like I said, I'm at a point where I don't think it's worth it yet. But if I really looking at, like, if I'm making some animal animations and it feels like that I need that actual optimization to make it look better, if I can notice it, then it's an issue. But if it's animated and you don't really notice it, then there's no point in doing that extra math in there. I can always do two versions. I can do 3 bone and 3 bone optimized. And I can which the optimized version will probably be for a certain character. Like maybe the main character had these uneven bones, but I want that to animate better. So I'll probably use the more optimized version, and then a wolf that's running around, I don't give a damn. I'll use a different solver for that one, which is does less math. But yeah, there you go. There is the 3 bone hind leg solver. And like I said, it works in the demo. So if you have an animal that's walking and the legs fold up just right, you can see it better at this angle. Whoa. There you go. So there we go. We have our 4 IK solvers, a single bit of animated data that it gets applied to all 4 different rigs. So like I said, in case you haven't seen the demo files, because I don't think I have been showing it to you, because like I said, it doesn't really matter. But the demo file is related, I'm really bad at just copy pasting and just leaving some of the comments alone. But as you can see, I just have one set of data, that ends up animating the IK target, and I just apply that target to a solver, then apply it to a pose. Solver, apply, solver, apply, solver, apply. So that is the magic here for the thing, for this thing. And there's nothing else in here. Everything's the same as the other files. And this is, I guess, the end of the line for me doing these IK solvers. I was thinking about doing one more IK solver, which has to do with fingers. Because I sat down and it's like, well, a finger works differently than a leg, so I can make a finger IK solver. So this way I can do an IK target, and then a finger actually rotates differently. So like the first 2 bones, like the last 2 bones in the finger are what's bends, but the first bone is what dictates if you're going to fold in or not. So if I'm trying to do like a pose like this, is different from a pose like this. So maybe down the line I might do one more IK solver where I'm going to animate an entire hand. So it'll be like a finger solver for like the 4 individual fingers, then maybe a solver for how the thumb works. So this way it's like that one solver can actually handle the 4 fingers. And then the extra solver will probably be the thumb, because the thumb has the bones in the different places and it rotates in different action. So I had like really some cool ideas of where I can just do animations like this and start doing like hand signs. So yeah, I had some ideas, but I think I don't want to do IK solvers for a while. I want to move on to something else. I want to start building an IK rig and maybe just start doing some walk animations. Redoing them again, but using the IK chains and whatnot. And I'm thinking about, I don't know if it's going to be successful or not, but I'm going to try to calculate the stride. And if you ever seen the Overgrowth GDC video where the guy showed you, like, explained how he did his procedural animations, he created something called a stride circle. So I want to see if I can build something like that. So I'm going to try to figure out how to do that based on an animation, analyze the animation, figure out the stride, and then use that stride to have a constant walking animation without actually me tracking care of the feet. Because I've done walking animations already where I track the feet and then I do actually move it physically based on the character. But that's more work. So I was thinking maybe to simplify simplify the velocity of a character, maybe it's easier if I can come up with ideas like what is the actual velocity of the character moving based on its stride, and then just move it and just animate, and hopefully that won't cause any floating feet issues. I'm also thinking about maybe doing the velocity, have the animation, then lock the foot onto the ground until it reaches near its maximum length. Then it pops off, and then it continues the animation. So I'm thinking about doing something like that. Right now, so that's where the next direction I'm going to go in, is like more start taking this information, start building the IK rig, and start doing with some walking animation, just 2 legs and a hip, and just see if I can create something that I can control and walk around, make it run, slow down, maybe do some jumping animations just with some 2 feet. So that's where the next direction is. So now that we got all these IK solvers, we got the IK chains, we got pose data, we got all this built. Now let's start doing some fun stuff with it. So that's why I don't want to do a hand now. Maybe I'll do it later. But if there's a big outcry that you guys want me to make an animated hand, I'll definitely give it a shot. It should be easier compared to everything else so far. So I just want to end it kind of like showing you this leg and copying this. So this is what the last couple of videos have been about. This has been what I've been doing for the last month. I've been trying to essentially create this. And like I said, that section that he just showed you, this is our IK data that I have animating. So that he has the exact same ideas. That's the IK data. He has applied it to a 2-bone rig. And then eventually he shows off that by using that one bit of animated data, which I have no clue what he calls it, he then can apply it to all these other bones. And as you can see, I have the 2-bone solver. I have a 3-bone solver. I have the piston. This is what I call the piston, so I would try to mimic this. Everything I did with the 3-bone solver can be applied to this, because like I said, these are all parallelograms, or so you can just, instead of just applying it with 3 bones, you just apply it to multiple bones. So that's why I didn't even bother, because I don't really want to waste my time doing that if I don't need it. Like I don't need that kind of solver, but the information, the way I did the 3-bone solver can be applied to this very easily. And granted, I didn't make this leg, but this leg is my circle arc solver. I can actually make this. Oh my god! So I can build this leg by just splitting the target distance in half, do one circle arc, and then do the other circle arc in the opposite direction, and then it makes a sine wave. So the hard part was getting the circle arc working. That's really the hard part. I'm sure there might be a really cool solution other than the way I did it to make this sine wave, to make the arc more to work with the sine wave. But like I said, I can probably go about doing it by using the circle arc and just cutting the things in half and just applying it. I think the only problem is that, yeah, as long as you don't go past 80 degrees, you're golden. So I don't know if that's what he's doing himself, or do he actually has a function which kind of creates a sine wave placement. But yeah. So like I said, I got pretty much all the legs working, and here's proof, and here's all the code. It's available on GitHub. It's free to you guys to use. I don't know what license. I think someone suggested MIT. I don't care. Like I said, in a circle arc, I just want this information out there for the collective, because if more people know how to do this, then we'll have more stuff like this, and we can improve it as well. So yeah, we got 4 legs. So the next step up is to start using these legs to actually animate our character. So now I want to see if I can use these IK solvers to start making walking and run animations. And then, like I said, maybe figure out how to do a stride wheel. So this way I can just move a character based on analyzing its stride. So once I have the stride, I know what the velocity is. And I'll probably animate it kind of just like how Overgrowth did it, where there's like a circle between the legs, and you can see the wheel move as the feet move, and I'll see if I can illustrate that as well. If I get it working, I want to see if I can just replicate that that thing. So so I might end up. My idea is that, like I said, I want to kind of do halfies between IK rigs from Ubisoft and Overgrowth's pose. How they kind of do all their animation just based on basic poses. But I want, for me, instead of having poses created in the tool, I'm probably going to just code my poses and then use that to alert back and forth and create the animations similar to what Overgrowth does. So yeah, those are my inspirations, and that's the direction I'm going. And a month ago, I thought I wasn't going to get this far, and I'm kind of happy that now at this point, it looks like I've gotten this far, and the future looks bright, because that means I got over that hurdle, which I think was probably the most complicated, because there's a lot of math. And if you're not new to the series, I never went to college. I don't know math that well. I'm learning this as I go, so I'm sure I'm making tons of mistakes. But again, you do what you can, and hope in the future someone can steer you in a better direction. But it's like, it's better than just not doing anything at all. So just do things. Just try to create something. Try to do it as best as you possibly can, and just whatever. And if you're like me, you want to share it and make the world a slightly better place and easier for game developers, I guess. Because I want to be a game developer. A lot of people give out free information. I want to give out some free information. So that's it. So yes, please like and subscribe. That helps the channel. One day, this channel will be monetized, so maybe I'll make some money on these videos. And again, I want to say thank you for all the new patrons that appeared in the past week or two since I started making these videos. I really appreciate all of my patrons that show up. Again, like if it's a really big deal for me to do a hand, I can probably spend a couple of days, maybe a week, and build up that new. The IK solver should be pretty simple. For a finger, it's the thumb that might be tricky, because it moves in odd ways. But like the other four fingers work. They're all identical, so it's pretty easy. So you do one, it works for four fingers, then you just got to figure out the thumb, and that's it. So but yeah, I'm pretty sure more people care about the Overgrowth way of doing things other than me just making hands. If anything, I'll challenge you guys to make a finger IK solver. Like I said, it's the first two bones. You just need to rotate about 90 degrees. The first two bones rotate 90 degrees, and the last two bones rotate up to a maximum of 90 degrees. The first bone will dictate the direction that you're going. So for me, I was planning to use the IK target data. Scale will determine how much of the 90 degrees to use for each finger. So I scale it. So if the scale is like close together to the actual target, that means I rotate the last two bones at 90 degrees, and based on where the direction is where I point the actual finger. Like I can basically probably use this hand better. So between doing something like this and something like this. I don't know if it's hard to illustrate, but so like if you sit there and just play around with your finger and just watch it and see how the bones rotate, you'll probably get what I'm talking about. Like I said, like if I keep the direction in the same direction and just bend as far as I can, it's pretty much just a 90 degree for the second and third joint of the finger. And it's that first bone, remember the one we always use for all our IK solvers to do the alignment? That one actually dictates if it's either like this kind of pose or it's a fist or some kind of in between. So yeah, just keep that in mind. Like if you want to use IK data, that's probably that's the direction I've been thinking about how to go about it. Like scale will determine how much to bend the finger, and the actual direction dictates where the first bone points. And there's a constraint. Just keep in mind that when your hand moves, the middle finger doesn't really move, and it's the other fingers that move away from it. So just keep that in mind if you're going to try to create an eye. Like I said, I spent a lot of time staring at my hands to figure out how how to animate my hands, and those are the ideas and the solutions I came up with. So if you guys really want to try it out, give it a shot. So this video is already 40 minutes too long. Probably the last 5 or 10 minutes have been BS. So yeah, I'll see you guys in the next video, and thanks for watching.